All right, so today we are going to discuss the rest of our intro to logarithms. So yesterday we did all the basic stuff, what a logarithm is, how to use our swoop method to convert to exponential form, how to press it in on our calculator, and how to write the different inverse equations. Today we're going to be focusing on the graphing aspect of logarithms. So we need to be able to graph logarithmic functions. Along with graphing, we need to be able to identify domain, range, asymptote of our logarithmic graphs. And then finally, because we're going to use our graphs to solve real-world application problems that involve some logarithms. So, anytime we do a type of graph for the first time, we talk about the parent graphs. And there's two here only because we have two different types of logarithms. Remember that this one is called the common log, where the base is 10 generally. And this is the natural log, where the base is e. So really on this one, we could just always put e there. Now, we have the same ideas here that we have had with most of our parent graph. H is going to represent a shift to the right or to the left. K is going to represent a shift up or a shift down from our original starting point. So, in general, these are our parent graphs. Now, things that are always going to be true, regardless of what the base is, regardless of the values of h or k, is that x equals h is going to be your asymptote. Now, notice that this is a vertical line. Exponentials all had horizontal asymptotes, meaning it was y equals a line, and it was a horizontal line that we graphed as the asymptote. Logarithms have vertical asymptotes. So when we write their equations for the asymptotes, we write x equals because it's vertical. And notice that it's h and not the k, again, because k represents a horizontal line, whereas h represents a vertical. Notice also that the domain and range idea has kind of flip-flopped. Here, it's the range that's always all real numbers, and the domain that changes along with the asymptote. In this case, we're going to have all reals greater than our asymptote is going to be your domain. Now, when b is greater than 1, that means the graph is going to move up and to the right. If you have a base that is between 0 and 1, that means as you move to the right, the graph is going to move down. So if you have a fractional base, so like this 3 here, if that were a 1/2, that would change the way that the graph moves. Now, when we get to C, this is going to come into play. If the base is something other than 10 for the plain log, you're going to have to do work by hand to be able to graph it. Because many of your calculators will not, in your graphing screen, be able to graph something that doesn't have a base of e or a base of 10. So I'll show you how to do that when we get to example 1c, because that's an exact example of this case. So that's this case right here. All right, so let's look at some of these graphs. Y equals log of x minus 3. So because no base is written, that means that the base is 10. This is our common logarithm. So you're obviously not going to know log of numbers off of the top of your head. So we can use the calculator for this to come up with our points. So you're going to type into your y equals screen, just hit the log button. If it brings up a parenthesis, great. If it doesn't, you need to add one, because this x minus 3 has to be enclosed together. If you get something that just looks like this, that's something totally different. That would be a k value of 3. We have to have the parentheses. So those are important. So type that into your y equals. If you still have a crazy window from the let's make a deal activity, then zoom 6 so you can go back to your standard window. Once you've got a picture of what the graph should look like, then you can come up with your table. Now, here, we know that because of this minus 3, that the original starting point, which would be 1, 0, generally we're starting at 1, 0, is going to be shifted to the right 3 places. So I should know, instead of 1, 0, I move right 3, 1, 2, 3. So I'm going to have a point right here. I should also know from this information up here that x equals h is my asymptote. So x equals 3 is where I'm going to draw, and again, it's a vertical line now, my vertical asymptote. So now I'm going to pick some points around this. I know that my domain is all reals greater than the asymptote. So don't pick an x value that's less than 3. It's not going to make any sense. It has to be bigger than 3. So let's say you start with 4. If I plug in 4, 4 minus 3 is 1. So you can either look at your table or actually press it into your calculator, log of 1. But if you're looking at the tables in the second graph screen, you should see that the y value is 0, which is exactly what we said. We shifted it from 1, 0, 3 to the right, and that is our point. When x is 5, 5 minus 3 is 2, the log of 2, your screen should tell you, is 0.301. When I plug in 6, 6 minus 3 is 3, the log of 3 is 0.477. At 7, I get 0.602. Now here's the part that's tricky for a lot of people. Most people get this part okay. And so they tell me 5.3, that's like right here, then 0.47, I'm almost to a half. I've gotten all the way over here and I'm just barely above a half. So I'm not going very fast in any direction. But I need to know what happens over here. And I can't pick x equals 3 because x equals 3 is not defined. It's not in my domain. X has to be bigger than 3. So you can let x be anything bigger than 3. So let's say we make it 3.5. Now that's not going to be in your table. If you've forgotten, when you pick values not in the table, you can still get your graphing calculator to work for you. You go to second trace, choice 1, select value, and then type in your number. So once I've got this graphed, if I want to know what the y value is when x is 3.5, I can simply go to second trace, choose choice 1, and then when it comes up, it'll come up on the graph screen, x equals, and you have to type it in. So you actually type in 3.5, and it's going to spit out the answer for you. So, and you could also do it by hand if you wanted to. Again, if you're set on the graphing calculator telling you, great. If not, just plug in 3.5. 3.5 minus 3 is 0.5, and the log of 0.5 is negative 0.301. So negative 0.3 is where I would be halfway through. Now, think about what an asymptote is. Remember that an asymptote, by definition, is a line that the graph approaches but never reaches. So that means when you draw your graph, make sure you do not cross the axis. The other thing that I get people doing here that I want to make sure you don't is I get people who try to make this look like a square root graph, and they've got something that just looks like this. You need this part right here. It gets exponentially smaller very quickly on this side, but yes, it is continuing on forever. You could plug in 3.00000001 and get an actual value there. So make sure your graph reflects that it's going on forever. All right, so now I just need to state the domain, range, and asymptote. So that should be the easy part. Domain should be all reals greater than my asymptote, which is exactly what I see in the graph. The only x values I have are those that are bigger than 3. So all real numbers greater than 3. My range should be all reals, which it is. It's going on forever negatively here, going on forever positively here, although very slowly. My asymptote, x equals, because again, it's a vertical line, 3. And there we go. All right, so let's look at another, and this time we're going to look at a natural log. We're using the same process, it's just we press the ln button instead of the log button here. So, circle those there. All right, so again, this is different than this. This does not have parentheses. Don't put them in, because if you put in parentheses, that's making 3 an h value, where this is intended to be a k value. This is a shift up 3. So normally, logarithmic graphs start at 1, 0, or in some cases, with natural log, it's going to be 0, 0. So this means I'm going to shift it up 3. So I start at 1, 0. I go up 3. There's my starting point. Now, my asymptote is x equals h. And there is no parenthesis. There is no h, which means h was 0. So my asymptote here, I'm going to go ahead and fill it in down here. My asymptote is x equals 0 because there was no h value. So that means my domain should be all real numbers bigger than 0. My range should be all real numbers. So let's make my graph happen, and hopefully it fits into these. So if my asymptote is x equals 0, that's the same as the y-axis, so drawing that in. And then I need to make my chart. So, again, I can't pick anything that's 0 or smaller. So I leave a space, but I start at 1, and hopefully I get 3. Again, you can look at the chart to help you come up with these values, or you can actually press in natural log of 1, close the parentheses first, and then do plus 3, and that's going to give you 3. At 2, I get 3.6. At 3, I get 4.1. At 4, I get 4.4. Notice how slowly these increase. Much, much slower than our other graphs. So 1, 3, 2, 3.6. 3, 4.1. And 4, 4.4. Now, I need something in here. And again, I can't pick 0. It has to be bigger than 0. Generally, I usually pick the half, but you can certainly pick anything you want. So if I plug in 0.5 for my x, so I do natural log of 0.5, and then add 3, I get 2.3. And it's about 2.31. So 0.5, 2.31. Again, when you connect it, make sure you don't make it look like a square root graph. Make sure you make it approach that asymptote but never cross it. So in blue there is my graph. All right, last one. These are the ones that I put the star by. These are the special case, because most of you, and some of you might have a newer version that allows you to do this, but many of you do not. And if you can't change this base, you're going to have to swoop into exponential form first. So this is a good opportunity to practice my swoop. I start with the base, I go around the equal sign to pick up my exponent, and I set it equal to this. So 3 to the y equals x plus 1. Now here's the key. When I pick 3 points, you are actually picking the y's first and finding the x's. So when I go to make my chart, 3 to the what equals x plus 1. So I'm going to pick values for y here and see what I come up with. So let's say that I pick y equals 0. When y is 0, 3 to the 0 is 1. So I write, and on these you're going to be required to show work. I write x plus 1 equals 1 as my work, and I didn't leave myself a lot of room here, but x plus 1 equals 1. And then I solve that for x. So subtract 1, x equals 0. So 0, 0 is a point on my graph. Now, you should still know where your asymptote is. Your asymptote here, if this is a plus 1, is right here at negative 1. So there's my asymptote. So I know that I can't pick 1, but I could pick negative 1/2 if I wanted to. And I already forgot, you have to pick the y. So 3 to the negative 1/2, and I'm just writing my work down here, 3 to the negative 1/2 equals x plus 1. So negative 1/2 power means 1 over the square root of 3 equals x plus 1. Now, you don't have to rationalize this. We're just trying to get a decimal equivalent. So actually type in and figure out what 1 divided by the square root of 3 is, which it's about 0.577. Then subtract the 1 from both sides, minus 1, which gives you an x value of negative 0.43 approximately. So at negative 1/2, I get negative 0.43. When y is 1, again, all I'm doing is plugging it into my exponential, my swooped. 3 to the first equals x plus 1. So when y is 1, my equation becomes 3 equals x plus 1. That one's super easy to solve. Subtract 1 and x is 2. So the 0.21, I graph 2, 1. When y is 2, 3 squared equals x plus 1. Now 3 squared is 9, so that means x is 8. So let's see if I can fit that on. 2, 4, 6, 8, and then y is going to be 2. Obviously, anything else I pick is going to be off my graph, so that is good enough. Again, when you connect it, please make sure you do so correctly. Don't cross the asymptote, but do draw it going on forever that way. And there we go. So now all we need is the domain, which should be all reals greater than my asymptote, which is negative 1. My range should be all real numbers. And my asymptote, we can see, it's right here, is x equals negative 1. All right, so there's our graphs. Last one should be really quick. We're just using our graphs to answer some real life problems. It says most tornadoes last less than an hour and travel less than 20 miles. The wind speed S, measured in miles per hour, near the center of a tornado is related to the distance d, measured in miles, that the tornado travels by this model. So S is wind speed, d is the distance it travels. 93 times the log of d plus 65 is how those are related. So our first question says, suppose a tornado traveled 16.2 miles. So let's think about what that means. That means D is 16.2. What was its approximate wind speed? So that's telling us to find S. So take our equation and let's plug in what we know. So S equals 93 log of 16.2 plus 65. Now again, be careful when you press this in. This should be super easy, but I always get people that put parentheses in the wrong place, and then it becomes difficult. For most of you, when you type in 93 log, it automatically opens a parenthesis. Only the 16.2 should be going in there, not the 65. So when you're typing this in on your calculator, it should look like this: 93 log 16.2, close the parenthesis, plus 65. And when you do that, hopefully you come up with approximately, it doesn't say what to round to, but let's just say 177.48. And it's wind speed, so that's measured, it tells us in miles per hour. So a tornado that traveled 16.2 miles had a wind speed at the center of 177.48 miles per hour. Then it says, on March 18th, 1925, a tornado whose wind speed was about 280 miles per hour struck the Midwest. Use a graph to estimate how far the tornado traveled. So we're trying to find D, how far it traveled, and we're told that S is 280. So if we look at what that is saying, that's saying 280 equals 93 log D plus 65. Now, you could solve this algebraically, and I'm going to show you that for those of you who prefer algebraic rule-based methods. You would subtract the 65, which is going to give you 215, equals 93 log D. Then divide by the 93, which is going to give you 2.3118 equals log of x. Then, because the base of the common log is 10, you would swoop to solve. So you would do 10 to the, oops, half my swoop went away, 10 to the 2.3118 equals x. So if we do that, you should come up with about 205 miles. Now, if you don't want to do it algebraically, the reason this is in the graphing section is because we can solve this by graphing. What you can do is, and I'm going to write or here because either method is perfectly acceptable, you can graph your y1 as the 280 that you know, and graph y2 as 93 log x plus 65. And then use your second trace intersect feature, which we practiced in our most recent group activity. Use your second, oops, I wrote interest, that's funny. How about intersect? Use your second trace intersect to find the intersection point. The x value is going to be 205 miles, which is your answer. So graphically, algebraically, you should get the same answer. All right, that is it for this lesson.